Lourens. We're going to talk about generalized ground state Ansätze from keyboard.
Yeah, I am Matt. I'm a postdoc at Stellenbosch University, which is in South Africa. And I'll be talking about this recent publication from me and my collaborators, who are Ilya Sanaisky, Hannes Kriel, and Ansätze. In this work, we present a method to find tensor network representation, structured tensor network representations for quantum many-body ground states. And hopefully it will be clear what I mean by structured as we go along. As we've heard a few times this week, the problem that we face when studying quantum many-body systems is that we require that the standard description of a generic state requires an amount of information that scales exponentially with the system size. Luckily, depending on the problem, the system you're studying, and the kind of questions you're asking, there tends to be a lot of redundancy in this description. So the goal then becomes to find an effective compressed description of the state you're interested in. And here by effective, I mean a description which preserves the essential physical features you're after, and one from which you can efficiently extract quantities of interest, such as expectation values of local observables and correlation functions. Okay, so as an example, when studying ground states, a simple ansatz is to assume a product state with minimal variational parameters, as is the case with meaningful theory. This will give you qualitative insight into the system you're studying, often at the expense of quantitative accuracy. On the other hand, you can use a fully numeric approach, such as tensor network methods. This will provide you with accurate ground state energy predictions, but you are stuck with a black box from which it's hard to extract qualitative insights. And the reason it's hard to extract qualitative insights is because these methods aren't optimized to expose the underlying structure in the states that they represent. So as a quick example of this, if we consider this Hamiltonian that was constructed by Affleck, Kennedy, Libb, and Tasakai, which is a spin 1 Hamiltonian, it famously has this exact matrix product state representation for its ground state. So I show the A tensors here on the left. So you can see that A plus and A minus is proportional to the spin 1 half raising and lowering operators, and A0 to sigma Z. Now, if you apply some variational technique on the system, you will not end up with the structured solution. You'll end up with something that kind of looks like on the right. And this is because of the gauge invariance you have in your representation for the state, which just means you can insert a matrix and its inverse anywhere on your tensor network. So this is where our method comes in. The basic goal is that if you apply our method on the AKLP system Hamiltonian, it will lead you to the structured ground state solution. So ultimately, what we want to do is we want to find ansatzes which is by minimizing complexity, but still preserving accuracy. Okay, so how do we do this? And what do I mean by complexity, since we somehow need to minimize it? I'll try and explain this by example. So consider these two bit strings on the left and right. Hopefully you'll agree that the one on the left is more structured than the one on the right. One way in which you can measure this complexity is by the length of the shortest program you can come up with to generate the bit string. So for the one on the left, you're just repeating 0, 1, 10 times. In Python, you can just write this as 0, 1 times 10. For the one on the right, you need a program that's essentially as long as the string itself. And this represents maximum complexity. More formally, this is known as Kolmogorov complexity. It just formalizes the idea that the string on the left is more structured than the one on the right. Now, I want to apply the same idea to tensor networks. And with this in mind, we developed a domain-specific programming language to generate tensor networks. So in this language, I generated these two networks, and the length of the program that generated the network on the left is much shorter than the length of the program that generated the one on the right. So I'm going to consider the one on the left more structured in this sense. The ultimate goal here is going to be to ask a computer to write a program that generates a tensor network to accurately represent a ground state and we are going to penalize the length of the program to minimize the complexity, and we're going to reward accurate ground state energy predictions. Okay. So, the details here isn't important, but I want to give you an idea of how this language works. So it's implemented as an open source Python package called hierarchical. In this example, if you look at the first two lines, I define a cycle and a mass, which is defined with this class Q cycle and Q mass. These I call primitives. Each has their own hyperparameters, which determine some rule on how to place a certain tensor along the circuit. And then in line 6 is where I generate this network. So it's basically a cycle followed by a mass repeated 3 times. The cycle is blue, the mass is red. And what the mask does, because of its hyperparameters, each time it hides half of the available indices or qubits of the sort of circuit. So all I really want to show you is that the language is compact. All I'm going to change in these lines just one hyperparameter of the mask, and then you get these similarly structured kind of networks. Okay. Maybe a better example is if you were to implement the quantum Fourier transform in this language. You would do something like this. I'm going to go through this line for line. So the first line says place atom on gate on top of the circuit. The second line says pivot a phase gate towards the top of the circuit with some functional relationship on the atoms. The third line says hide the top input from the rest of the circuit. And the fourth line says repeat this n times. Now this gives you the general n-qubit implementation of the quantum Fourier transform. So if I initialize this QFT object, which is defined on line 4, on 3 qubits, I get a 3-qubit QFT. If I initialize it on 5 qubits, the same QFT object, I get the 5-qubit quantum Fourier transform. Now you see we obtain an algorithmic description of this state. And what this gives you is this kind of size scaling property, so that so it automatically knows how to scale with system size. And when we're studying ground states, this will be important. Okay, so the method. We use evolutionary search to construct these Ansätze. How this works is you start with an initial pool of primitives, each with randomly initialized hyperparameters. Each generation you run on a subset of the population. You have them compete against each other. Then you select the 2 fittest individuals and mutate and cross them over in various ways. You throw these new mutations then back into the pool and have it evolve. The way in which we evaluate Ansätze fitness is we favor accurate ground state energy predictions. Sorry. Okay. And then we also penalize the complexity of the Ansätze. We penalize the variational complexity and the structural complexity, which is essentially the length of the program. Okay. And this is also where that size scaling property comes in that I was talking about with the QFT. Because the Ansätze knows how to scale the system size, we're able to evaluate Ansätze fitness over multiple system sizes. So this gives you a few nice things. For one thing, it's more computationally efficient because you can consider small systems, which then the Ansätze you get out, you know how to automatically extrapolate to larger system sizes. And also it stops from finding Ansätze which overfits a specific finite size effect. So thereby capturing robust ground state features. Yeah, and then I'll talk in a bit about how restoring symmetry is coming into play. It should move less. And one other thing is you give your primitives an initial operator pool to use during the search. So this is the gates that it places along the circuit. For this specific experiment that I'm going to talk about, we use complex exponentials of Pauli spin matrices. So we're essentially searching for. See, maybe. Okay. Yeah. Okay. We consider two prototypical quantum spin models. In this system. Okay.
Might be the cable.
Okay. Now. Hold it. Okay. So consider the thin mesh of Hamiltonian and the trapezoidal Eigen model. The model has multiple interactions with a transverse field. Eigen model has nearest neighbor interactions with the transverse field. So applying our methodology on both these models, we look at the same ansatz independently, indicating some degree of universality. This ansatz has a very simple interpretation. It's well known that for both these models, the mean field solution is a single layer of Y rotations, sharing one variational parameter. We see that our method implements the mean field solution and then extends it to incorporate correlations with these Y rotations. This ansatz is also retractable. You can represent it with this matrix product state of one dimension 2. I show the A plus and A minus matrices down here. And then you'll also notice that this lone B matrix here in the trace, that the state that the ansatz generates is not translation invariant. So more generally, we found this to be the case. Our method would find ansatz which tended to break the models under symmetries. But because we are analyzing the complexity of the ansatz, they tend to be analytically tractable, and we can restore these symmetries by hand. So in this case, that's what we did. We just replaced the B matrix with an A matrix. You get a translation invariant ansatz. And then, for example, for the LMG Hamiltonian, there's two other symmetries. We also break parity and swap symmetry, and we restore these analytically by projecting to the relevant symmetry subspaces. Yeah. So the results. Here I plot the root mean square magnetization for the LMG model. This is the predictions of our symmetrized ansatz. The open squares represent exact results, and the solid dots is our ansatz prediction. So we see that we capture finite size effects very accurately. We also reproduce the exact root mean squared magnetization in the thermodynamic limit, correctly predicting a quantum phase transition at 1/2. If we look at the relative energy errors, so in dashed lines here, I show the mean field energy errors, and in solid lines is that of our ansatz, the symmetrized one. Red corresponds to the critical point, light and dark blue to being deep into the ferro and paramagnetic phase. So at worst, our ansatz has a relative energy error of 10 to the negative 6 for around 20 spins, and this goes down to exactly 0 in the thermodynamic limit. And we improve upon the mean field solution by at least 3 or 4 orders of magnitude. Now, while the mean field solution also becomes exact in the thermodynamic limit for the ground state energy, if you don't symmetrize the ansatz and optimize for the larger limit of the optimal angles, you get a product state, so you get the mean field solution. If you symmetrize the ansatz and then take the larger limit and optimize the analytical solution, you don't get a product state. You're left with a state with a non-trivial amount of entanglement, and this actually reflects the exact LMG ground state. So the mean field only probes limited ground state features, and yeah, our model was able to capture this. Yeah. To test the robustness of our approach, we tried a different operator basis. So all of the terms of performance basically a quantum circuit. Using real exponentials of ladder operators, we find more general tensor networks, so normalization factor in the states that we produce. We were again able to find an ansatz which is equivalent in accuracy and complexity. This time the ansatz is translation invariant, and you get this nice matrix product state representation where you can now start playing the game with restored symmetries. If we look at the computational cost, basically, if you consider a system size group of 3, 4, and 5 and have 8 CPUs, it will take about 50 minutes to find the ansatz. If you consider a size group of 19, 20, 21, it takes an hour and 50 minutes. But I should mention that we always found the same ansatz independent of which system size group you considered, so you were fine with just using the smallest group. In terms of memory, if you use about 4.5 minutes, if you assign You assign one worker to each CPU and have 8 CPUs. And for 1921 group, it uses up 8.5 gigs of memory. Okay. We also tried some other applications. So trying to find an ansatz to perform quantum phase recognition. So this is a clusterizing Hamiltonian. We know ground state can be in one of three possible phases: paramagnetic, antiparamagnetic, and symmetric topological. So we want to find a quantum circuit in this case that tells you whether an unknown ground state is in the STP phase or not. Yeah. The top circuit here is the circuit that our method finds, and the bottom one is what we compare against from this publication from Comchen and Lucan, where they introduced this variational ansatz for this problem. To look at the results, so our ansatz requires 11 variational parameters, whereas theirs require 1,308. We do produce a sharper phase diagram, so on the left is theirs, and on the right is ours. And I use the same colors here. If you look at these other metrics, the sample complexity tells you how many measurements you need to perform to be 95% certain you are the STP phase. So for the sample complexity on the inside, which is you're on the phase boundary but inside the STP phase, so that's where you want to be accurate. We need almost half the amount of measurements that they would. For the sample complexity in the middle, we need about 2 or 3 more measurements, and the SE is very comparable. Okay, the last application we did was trying to rediscover quantum algorithms. So we were able to rediscover the Deutsch-Jozsa research and quantum Fourier transform. I found the general n-qubit implementations again. So on the right here is the typical textbook version of the algorithm that we find, and on the left is what's produced by our algorithm. What's nice here, again, because of the size scaling property, we only needed to consider circuits up to 6 qubits to find the general n-qubit implementation. Yeah. And so I just show an example of what one evolutionary tree looks like. So this is for a successful Grover's run. It's nice to see that, like, over a year, you find quite a fit ansatz, but then you need to perform a mutation to lower the fitness to ultimately find the correct solution in the end. And we also in this work compared the fraction of the search space we are exploring with our algorithm. So we defined a search space size as the maximum number of evaluations that you need to do for a root cause search using our language. So it's a lower bound for the actual size. And then we compare it against the actual number of evaluations we did during the search. So you can see that it's several orders of magnitude less that we needed to evaluate versus the actual size of the space for all 3 algorithms. And I'll stop here. I'm happy to answer any questions. Thanks.
Much. Is there a question? Yeah, what did you do about APLT? You mentioned at the beginning that you.
Yeah, so I mean, I run the same search. I found like a cycle of this exponential of what was it, the sigma plus and the sigma minus with 1 parameter, and then if you then look at the actual NPS, it's very close to the exact one, but it's not exactly. And then based on like some parity argument, you can like make one of the matrices just equal its own transpose, and then you get the equality ground state. So this was a quick thing.
Can you compare your complexity of finding the NPS? Okay, the NPS is not for the APLT, but in terms of parameter search, you had like a graph, right? So I think for a different model, but is you train your evolutionary search, and then the winner of this evolution is sort of a parameterized ansatz, right?
Yes.
And can you compare